So I want to welcome you to the Feed the Future Innovation Lab for Small-Scale Irrigation semi-annual research meeting. The presentation that you're about to see has been based on research conducted with the support of USAID. Our presenter is Yuhun Dile from Texas A&M University. He's an assistant research scientist. And I will hand over to you, Yuhun.
Thank you very much for inviting us for this presentation. So I will be presenting on the impacts of scaling small-scale irrigation on nutrient loading to freshwater ecosystems in Ethiopia. And this is a collaborative research between researchers at Texas A&M and IFRI. And the collaborators are all doctors, Dr. Abiyu Kalul, Dr. Jean-Claude Bezimana, Arsi Nivasan, Nicole Lifor, and Dr. Neville Clark from Texas A&M, and Hoashi and Liang Yu are from IFRI. So our field research has shown that small-scale irrigation can improve agricultural production, it can improve environmental sustainability and household income and nutrition at household and at field scale. For example, the field scale research that you see here at the right corner shows that small-scale irrigation of 100 millimeter can give about 25 ton per hectare of tomato. But as the irrigation increased up to 400, for example, we can optimize the yield and get more than 35 ton per hectare. And also, we also show that use of fertilizers and technologies can improve the profitability of the farmers. So as you see in these CDF charts, as we go into the right, that shows the profitability. So in this case, use of fertilizers and pumps and row and washer shows that the productivity of using those technologies increase. But our research also includes large-scale analysis where we look at the potential, the available land and water resources available to scale small-scale irrigation in Ethiopia. So the one you see in the right is a suitability analysis that we do. Actually, that work was done by Dr. Abiyu Kalul. And in this, we use different factors like land use, soil, climate data, population density, market access, and we factored weight in and overlaid, and we found that more than 12% of the rainfall land, which is about 6 million hectares, is suitable for small-scale irrigation in Ethiopia. So in this map, the green areas where, for example, the suitability score is more than 85, we class them as highly suitable. But as the suitability score decreases, we classify it as less suitable. But the cutoff was about 85. And also we show that using our SWOT modeling analysis, we see that there is a lot of water resources potential in Ethiopia. So the blue and green water, blue water is the water in rivers, lakes, and in the groundwater, and green water storage is the water within the soil moisture, which are all important for small-scale irrigation. So we see that more than 33% of the country has a blue plus green water storage of more than 400 millimeters. So as you see from that field scale analysis, an irrigation of 400 millimeter can provide a significant yield, high productivity in that case. So there is high potential of land and water resources to scale small-scale irrigation across Ethiopia. So while we assess the available land and water resources, we also estimated the potential for producing vegetables, lentils, and fodder in the rain-fed land. Because the white area you see here is either it's a grazing land, or it is a forest land, or it is an urban area. So we were simulating dry season vegetables, lentils, and fodder in those rain-fed lands. So from these two figures, you can see that using small-scale irrigation, we can produce more than 5 ton per hectare of cabbage in a large part of the country, and also more than 2.5 ton per hectare of onion in a large part of the country, as you see from the maps. But this production was using irrigation, but also applying fertilizer. So this is a case where farmers, those who are producing dry season vegetables, lentils and fodder, are applying currently. So urea is a nitrogen-based fertilizer, and DAP is a nitrogen and phosphorus-based fertilizer. And in some cases, the farmers, for example, in the case of cabbage, they applied more than 200 kilogram per hectare fertilizer combined. But in the case of lentils, they don't apply fertilizer. But in the case of veg, which is a leguminous crop, they apply DAP. But this fertilizer is applied on top of the fertilizer that is applied on the rain-fed season. So in the case of major cereal crops that are cultivated in Ethiopia, generally the farmers apply more than 100 kilogram per hectare of combined urea and DAP. So this is a large amount of fertilizer applied, and we were interested, will application of fertilizer for the dry season crops increase or decrease environmental hazards? Will it increase nutrient loading or not? So that's what I'll be presenting today. And the work was done using SWOT model, aggregated SWOT model. I will not be talking more about the model, but we use really fine resolution climate data, more than 240 rainfall data and 140 temperature data, fine resolution soil data, land use data, and also the hydrology and the crop simulation were calibrated using locally collected crop information, hydrological information, which is obtained from our partners in Ethiopia, from the Ethiopian Institute of Agricultural Research, FAO, and other partner institutions. So the nutrient that the SWOT model generally simulates are related to sediment yield, which is a pollutant by itself, and also nutrients related to nitrogen, whether it is organic nitrogen, inorganic nitrogen, organic phosphorus, inorganic phosphorus. And we also track how those pollutants are moving in the landscape. So all those analyses are included in the model, but for the sake of this presentation, I'll be categorizing nitrogen-related nutrients are summed up together and will be presented as total nitrogen, and phosphorus-related nutrients are summed up as total phosphorus. And this is the case for cabbage for total nitrogen simulation. So the one in the left shows you the baseline situation. That is where only rain-fed agriculture is practiced. The one in the right shows both. There is rain-fed agriculture, but the farmers will be cultivating cabbage, for example. So, and this is long-term average annual total nitrogen loading. So you can see that those yellow and blue areas are becoming red. So there is an increase in nitrogen loading due to the implementation of small-scale irrigation of cultivation of cabbage. And from the box plot, you can also see that the median is increasing. So generally, we observe that the average spatio-temporal annual total nitrogen loading may increase by 22.12 kilogram per hectare compared to the baseline situations. And also, we found that this is statistically significant, and the 95% confidence interval ranges between 20.5 and 23 kilogram nitrogen per hectare. And when it comes to total phosphorus, there is a decrease in total phosphorus for cabbage when cabbage is simulated. And the decrease is due to the consumption of the residual phosphorus in the baseline situation by the crop. Basically, we have the rain-fed season, so all of the nutrients may not be consumed by the rain-fed crop. So some nutrient may pass over into the dry season. So, and also phosphorus was also added, but the cabbage was consuming, and there is a minor reduction in phosphorus loading when we were cultivating cabbage. And the decrease was about, it is small, 0.72 kilogram phosphorus per hectare. When it comes to onion and total nitrogen simulation, we see that there is a significant increase in total nitrogen loading. And you can see that in the box plot also, it is really a significant difference. And the increase in total nitrogen loading is about 26.56 kilogram per hectare. And that is because cabbage was covering the land and it's also consuming a large part of the nutrient compared to the onion. But in the case of onion, most of it is going through the surface runoff, through the groundwater, and also it is leached from the soil. As a result, the loading due to onion cultivation is higher. So the total phosphorus, there is a minor increase, but it wasn't statistically significant. You can recognize the difference in the median in the box plot as well there. And the increase was only 0.14 kilogram phosphorus per hectare. Yeah, with pepper also, we observed there is an increase, and the increase in total nitrogen loading was about 5.1 kilogram nitrogen per hectare. It wasn't like the other vegetable crops, but there is an increase in total nitrogen loading. Again, with the phosphorus, the change was minor. There is an increase, but the increase was minor and it wasn't statistically significant. And the spatio-temporal increase was about 0.14 kilogram per hectare. In the case of lentils, as I showed in that table, no fertilizer was applied. And what happens in the case of lentil was that there was a reduction in total nitrogen loading because the lentils were consuming the residual nitrogen from the rainfall season. So as a result, the reduction was about 5.59 kilogram nitrogen per hectare. And also for phosphorus, there was a statistically significant reduction. Again, the lentil crop needs nutrient and it was consuming the residual nutrient, and there was a decrease in phosphorus loading by up to 1.12 kilogram phosphorus. But when it comes to veg, as I was indicating, veg is a legume crop. It fixes nitrogen, and the farmers also added about 550 kilogram per hectare DAP, and DAP has 18% nitrogen and 20% phosphorus. So, and also veg is fixing nitrogen. So the loading with the cultivation of veg was significantly higher compared to the baseline scenario. And also you can see in the box plot, there is really a significant increase. And the increase in nitrogen loading due to veg cultivation during the dry season was 50.2 kilogram nitrogen per hectare. And also in the case of phosphorus, there was a reduction. Even if a little bit of phosphorus was added, the veg crop was aggressively consuming the phosphorus, and there was a reduction in phosphorus loading, and the reduction was about 1.81 kilogram phosphorus per hectare. So the simulation analysis that we do, the suitability analysis, the biophysical modeling is used by the agent-based modeling, and that agent-based modeling applies a constraint on the water resources availability and economic profitability, and we assess the impact of scaling small-scale irrigation. So this is a framework for the agent-based modeling. So the agent-based modeling basically accommodates the SWOT modeling and the suitability analysis. So the suitability analysis, as I say, uses land cover, soil, climate, topography, population data. The SWOT model uses biophysical data and also management data. Then the SWOT provides the crop yield that I was presenting, the irrigation water demand, we calculate that and we provide them, and also the available water resources, the water that could be used, and also the available water resources. And the suitability map is also fed into the agent-based model. And then the agent-based model, with those constraints, estimates the probability of adoption. So you can see that a large part of the Lake Tana area, the Amara region, in the Oromia, in the Rift Valley Basin, those are green. So there is high adoption, probability of adoption of small-scale irrigation in those areas. And then in this adopted land, if small-scale irrigation is actually implemented, what would be the environmental and economic impact is what we will be looking. And from this analysis, this is actually work by Hoa, and he shows that adoption of small-scale irrigation may cause water scarcity. Again, in the Lake Tana Basin, somewhere in Oromia, there will be a probability of water scarcity. And then the nutrient modeling was also ingested into the agent-based modeling, and then he estimated the loading at sub-basin level. So sub-basin here is 10 kilometer by 10 kilometer, and the loading can be more than 700 tons per hectare. When I go into the concluding remarks, we see that the loading, both nitrogen and phosphorus, depends on the type of crop that we are cultivating, because each crop has different characteristics and the applied nutrient. So in the case of vegetables, for example, higher amount of fertilizer was applied, and especially the loading for nitrogen was statistically significant. But in the case of lentils, lentils is also a legume crop. That's why they didn't add fertilizer. But the lentil was consuming the nutrient and there was a reduction. But veg, fertilizer was added. It was also fixing the nitrogen, and it causes a higher loading. But when it comes to phosphorus, generally the soils in Ethiopia have low phosphorus from previous research that we found. And because of that, the added fertilizer really didn't cause higher loading. In fact, some crops were consuming the residual phosphorus and there was a reduction, even if it wasn't that statistically significant. I wasn't presenting the results for sediment. What we observed was implementation of small-scale irrigation reduced erosion. That is because there is crop cover during the dry season. And if a rainfall comes in the dry season and if there is no crop, the erosion would be higher. But because of the existence of those small-scale irrigation crops, any rainfall coming is not causing erosion. So because of that, the erosion was lesser with small-scale irrigation. So from the analysis, we found that lentils generally, they require small amount of water. We didn't apply, and it's not recommended to apply fertilizer. They give a reasonable amount of yield. They are not causing higher amount of loading. So it looks like cultivation of lentils using small-scale irrigation is highly productive and also environmentally sustainable. But cultivation of veg requires special attention. Veg is a legume crop, it creates nutrients and then it's causing loading. So maybe the best approach for cultivation of veg is not applying fertilizer, so that excess fertilizer will not go into the freshwater ecosystems. And from this study, we found that maybe improved nutrient management, for example, implementation of filter strips, strip cropping, conservation agriculture may reduce the nutrient loading. Also, the fertilizers the farmers currently applying are based on recommendations by the agricultural extensionists or researchers and things like that. So that may not be the right fertilizer recommendation. And also in Ethiopia, there are only two types of fertilizers, urea and DAP. Maybe having a different type of fertilizer that ATA is working on with micronutrients and things like that may reduce the loading into the environment. Thank you.
Thank you very much, Yehun. You already have a couple of questions in the chat box, but I'll go ahead and call on people to read out their questions. Fitsum, you had a question?
My question is probably silly, but what I'm saying is nutrient loading in the soil or in the water bodies? What does it mean spatio-temporal?
What's the last statement you said?
You mean spatio-temporal?
Yes, yeah. So we used a grid-based model. So in those grid-based, that means in the field, in the field, we applied the fertilizer. So the way what works is first we simulate things in the land, in the field, in the landscape, and then that moves into the rivers. So it is not, this loading is not in the rivers, but this is the potential nutrient which will go into the nutrients. Then we will have another layer of analysis also. In the rivers, there is also nutrient cycling, there is degradation, and there is also routing, so that will come. But this is the way the agent-based model works is at grid-based level, at landscape level. So we were providing the outputs at that level, at the landscape level. So this is a potential nutrient which will go into the rivers from each pixel of land, which has a grid of 10 kilometers by 10 kilometers. And it is a very nice question.
I think we also have a question from Malcolm.
If you have considered different irrigation practices to simulate the nutrient loading or leaching. For example, the difference between flood irrigation, drip irrigation, or sprinklers, nutrient loading.
Thank you, Malcolm. That is a very nice question. Yes, based on the irrigation technology, the loading could be different. So in this case, that irrigation technology depends on their efficiency. So what we used was a 70% irrigation efficiency, and that is generally for kind of furrow irrigation. So we accommodated the technologies through the irrigation efficiency, and that was 70%. But I think with different levels of efficiency, we can look at it. That mainly affects the surface runoff, really. The surface runoff may increase the nutrient loading, but with this small scale irrigation, the surface runoff is not too much. I mean, for small scale, but if it is large scale irrigation where they have furrows and it washes off the soil, the nutrient will go with that. So we use an irrigation efficiency of 70%, which is for surface irrigation. But that's a good one. We will think more into it.
Thanks, Yehoon. I actually have a question myself. I was wanting to understand better where you got the amount of fertilizer being applied. Are these the recommended amounts, like official recommended amounts, for example, from Extension or from another source? Or are these the amounts that you have gotten from data collected that shows what farmers are actually applying?
Thank you, Nicole. That's a good point. So these rates, we got them from our field research in Robit, Dangishta, Lemu, Adami. So in those sites, there are fertilizers that are applied in those field sites. So these are the nutrient amounts that were used in the Apex modeling. Abu, you may weigh in on that, but generally it is a lesson learned from the field experiments, and they are recommended by agricultural extensionists or university researchers.
Is that also the case for vetch, which we can see appears to be using a fertilizer beyond what might be needed? I may be saying that incorrectly, but it's clearly the one where there was some concern and where maybe the amounts being used wasn't necessary. So I was interested to understand a little bit more about what might have been recommended, and if this is actual data from what you've collected from the field in terms of how much farmers are using.
Yes. So, for example, for the case of the rainfed, we use data from the Central Statistical Agency. So that is widely used by the farmers, and it is averaged across the country for those specific crops. But like the veg, pepper, cabbage, it is data we got from the field. But as you are indicating, we are discussing to look at different rates of fertilizer, which provides reasonable yield, but which will also reduce nutrient loading. So like those fertilizer functions you develops at field sites, we will be doing that for the entire country. So that's what we have been discussing.
Thanks, Yuhun. I see Malcolm has his hand up again. Sorry.
Yeah, let's listen, Malcolm.
Malcolm?
Just to add to what Nicole mentioned, with regard to veg, we don't recommend application of nitrogen fertilizer, but a small amount of DAP fertilizer is recommended in our case. So maybe that's why the nutrient loading is very high when the normal crop nitrogen requirement is applied to veg crop.
Yes, Malcolm, you are right. Farmers are applying DAP. Generally, we say DAP is a phosphorus-based fertilizer. But when you look at the nutrient content of DAP, 18% is nitrogen and 20% of it is DAP. So within DAP, even if we say like in Ethiopia it is a phosphorus-based fertilizer, it has nitrogen in it. 20% of it is nitrogen. So that somehow plays in the background. Yes, and they didn't apply urea, which is exclusively nitrogen, and it is 46% of that fertilizer is nitrogen. So that's why I was bringing the fertilizer recommendation. Like there are two fertilizers and their nutrient level is really anchored, and we do not have the flexibility to change that. But of course, I think from the simulations, we see that we need to reduce the DAP amount. Perhaps if DAP has more phosphorus, or if it is entirely phosphorus, that would have been great. But within it, it has nitrogen.
Thank you, Yuhun. Thanks very much for the presentation. And if there's no other questions, is there any other questions?
Yeah, Srini here.
Okay.
Yuhun, in the analysis that you've done on the nutrient losses, did you look at the entire year, or you're just looking at only the dry season?
The entire year, because as you know, there is a residual nitrogen coming from the rain-fed season. So that affects the nutrient cycling and the simulation. So it is average annual.
Okay, I think, I mean, it's okay, but I think for this particular study, it may be worth looking at only the dry season, because the wet season is going to be happening regardless of what happens actually. But addition of the dry season, additional fertilizer and the crop and growing during that season, and the irrigation and so on, irrigation management and so on, it may be a good idea to just look at amount of loss of nutrients from the field during the dry season crop, meaning when it is planted or when the fertilizer was applied during the dry season until the season was over actually. And then you can also look at the residual that's going to be left in the soil for the next season, for example. That might give you a lot more clearer picture of the impact of the dry season or impact of the irrigation, agriculture, and so on and so forth. The second I would also recommend is looking at separating out the sediment-bound water quality to water-based or water dissolved water quality, meaning the nitrogen and phosphorus that is dissolved, like nitrate, ammonia, and things like that, and then sediment, organic nitrogen separately, so that you can look at the overall where you need to make improvement in order to reduce the footprint of nitrogen, nutrient losses to the receiving water bodies and receiving ecosystems and things like that.
Thank you, Professor Srini. Yes, I think we will consider both. In this, for the second one, we did that analysis, and we know in which type of the nutrient more nutrient is coming due to this irrigation or not. So we have that analysis, but for the sake of this presentation, I was aggregating them. Otherwise, we did that presentation.
Okay, I do not see any other questions, so I think we'll go ahead and end here. Yuhun, thank you very much for your presentation, and thanks for everyone for joining us today.